Hi everyone, welcome to the lecture series on advanced structural analysis. In this lecture, let us discuss the stiffness matrix method for frames, particular to sway frames. So let us identify a frame with a sway. So this ABCD is a frame with a lateral load of 50 kilonewton and a gravity load of 30 kilonewton per meter. We need to analyze this frame for stiffness method. Now the first step in this is to identify the kinematic degree of indeterminacy, and also called degree of freedom. So now this frame, because of this lateral load, will go to laterally to the right. So something like this. So if I draw this frame again, something like this. So the deformed shape of that frame may be something like this. Assuming that the beam is laterally, of course, due to this lateral, this is deformation. That means there will be a displacement delta. There will be displacement delta which will be same, assuming that this member BC is rigid enough to not cause displacement vertically. Okay. Like this. Then there will be a rotation in the joint and rotation in the joint. Okay. So at joint A, no rotation, no translation, so 0 degree of freedom. Here one rotation, one translation x direction, which is u, and one is theta. Here one u, which is theta. Here 0. So there will be 2 and 2. But because of this beam rigid, so the lateral translation u here will be same. So that is why we can take one common degree of freedom. So we have this, let's say u1, u2. So u1 equal to u2. So in net, so I have a theta b and 1u displacement and theta c. So this is the degree of freedom. So total 3 degree of freedom. Once you identify, so write down the displacement. We'll write down the displacement or the degrees of freedom on the structure. So by retaining this, so this is one of the theta b1 degree of freedom, and u displacement in lateral direction is another. So let us say 1, which is 2, and third one 3. So these are the 3 degrees of freedom. Okay. So I am giving this as a first degree, this is a second degree, and this is a third degree. So these 3 are the coordinates. Now once you understand this, so due to this external load applied on the member, if at all on the member, That means this is only load acting at the member, which is 30 kilonewton per meter, where this joint is fixed, this joint is also fixed, and this 50 kilonewton load is at the joint, which will not produce friction moments in the beam. So we need not. So if say A and this is B, C and D, MFAB is 0, which is equal to MFBA. MFBC is minus 30 into 4 square by 12. Okay, which is equal to minus 40 kilonewton meter, which is equal to minus MFCB, and MFCD is equal to 0, which is equal to MFDC. And from this what we can understand, if you look at MFBC, MFBC is a movement at this point. This is a movement at this point. MFCB is movement, MFCB movement here. Okay. Now my coordinate is there only. So at this MFBC I have coordinate 2, MFCB I have coordinate 3. So and I also have a load, direct load at a coordinate one direction. Okay. Now, so P2L is equal to minus 40 kilonewton meter. P3L is equal to 40 kilonewton meter. Okay. Now, so these are the friction moments due to this external load after joints made restrained. So now the stiffness coefficients for each of the coordinates. So let us see. I will draw this structure again. This is 2 meter, this is 4 meter, and this is 4 meter. Okay. Now my coordinates are one coordinate, second coordinate, and third coordinate, and we have to assume that these are fixed. Now let us look at unit displacement at coordinate 1. So we are trying to find out the stiffness coefficients. So now due to this unit displacement at 1, so what will be the load or shear at 1? So let us say this is A, point B and C and D. So if I try to draw the effect of this unit displacement applied at joint B laterally, so what happens? The structure deforms like this, and this member remains as it is, and structure deforms comes like this. Remember, so there is no, this is fixed still joint, the joint still fixed. Now what I did, I have applied a delta displacement which is equal to 1, and this also cause same amount of delta here in the column 2 also, right? So due to this unit displacement here, how much will be the force or shear at coordinate 1 will be nothing but my K11. That means if I just take a like this, if I apply unit displacement here, you get this unit displacement delta equal to 1. How much is the shear? Means how much load I have to apply to make deflection here equal to 1. Yes, very important. So we are looking for a shear here. The force is nothing but a shear here. So that we already learned during slope deflection methods, that when I have delta, when a beam is deforms a delta amount downward compared to the left hand support, so the moment produced in each of that moment produced is 6 EI delta by L square, 6 EI delta by L square, both sides, both are anticlockwise. Okay, so moment produced is this, but what I want, I am looking for shear here. So the shear will be, the shear force at this point will be taking moment at, let us say, point A. So taking moment point A, so 6 EI delta by L square plus 6 EI delta by L square, anyway delta equal to 1, 6 EI delta by L square plus 6 EI delta L square plus shear force, that is a VD. So VD into length of the member, right, equal to VD into length of the member. Okay, so the VD will become 12 EI delta by L square by L, that becomes 12 EI delta, anyway not there, delta 1 by L cube. This is the shear force developed in the joint B, which is the coordinate direction 1. So that is, I have to say, K11. So this is nothing but my K11. Is this clear? So now onwards you should remember, when a unit displacement applied at a point, at the same point the shear corresponding to displacement is shear, the shear produced is 12 EI by L cube. Very important. Now, so I will write here K11 is 12 EI by L cube. L is your 4 meter. Okay. Now, due the second. Now we are saying that displacement at 1 effect at 1, that is K11. So displacement 1 effect at 2. So I also have a coordinate like this, second coordinate. So due to this displacement 1, how much is the movement produced at a 2, which is nothing but movement produced here. So we already said, due to the unit displacement and delta displacement downward, delta which is equal to 1, the movement produced, if it is right hand side, so minus 6 EI delta by L square, so 6 L by L square. So that movement is nothing but your 6 EI by L square. So that is your K21. So K21. So which is your 6EI by 4 square. Now, due to unit displacement at 1, how much is the moment produced at coordinate 3? Same, delta 1 here and delta is same thing. So this becomes K31, which is 6 EI by L. Here length is 2 meter, 2 square. So these are the stiffness for unit displacement at coordinate 1. So let us look at what will be effect due to unit displacement at coordinate 2. So I will have to write down K12 and K22, K32. So K12 is also called K21. So I can directly write 6 EI by 4 square. Okay, 6 EI by 4 square. One correction we need to make it here. The K11 is the when unit displacement apply here, the stiffness is shared by this side column also. Both columns will share the resistance to the delta. So that's why I have to add 12 EI by 2Q, because both the column will offer resistance to the unit displacement to the right side. So I need to add the resistance or moment resistance for the second column also. Okay, now, and since this displacement is right hand side downward, which is taken as a minus 6 AL square, so I have to take minus, this also minus, then K22. So due to the unit rotation at 2, how much the movement produced at 2? So very simple. So we are directly going by as I told 4 EI by L for each joint, because the joint is getting rotation here. So look at here. So this joint rotated unit. So this column and this beam both got affected with the 4 EI by L. So 4, the same direction, 4 EI by L of the column, which is 4, plus 4 EI by L of the beam, which is also length 4, which is 2 EI. K32, that means when I apply a unit displacement at 2, how much is the moment produced at 3? So which is half of this beam movement goes there. So this movement is 4 EI by 4, half of that 2 EI by 4, which is 0.5 times EI. So things are clear. So let us go to the next. Now I am going to apply the unit displacement in coordinate 3. When I apply unit displacement in coordinate 3 direction, that means I am applying unit rotation. So I need to get the effect at each of the coordinates. So 1 3, k2 3, k3 3. So due to this unit displacement at 3, how much is the displacement at 1? Or another way to say, how due to unit displacement at 1, how much effect at 3? Both are same. That is at k13 equal to k31, which is nothing but minus 6ei by L square. So that k13 displacement here, so k13 is k31, which is by L square, which is here. Due to that, this column length is 2, so 2 square, which is minus 1.5 ei. K23 is equal to K32. Okay, K23 means because of the displacement, unit displacement at 3, how much is the moment produced at 2? Half of this beam. So this is 0.5, same, equal to K32 is equal to 0.5. You can say 2ei by 4, which is 0.5 ei. Then 3 by applying a unit rotation at 3, how much is the moment produced at that same point? So this joint has two members, beam and this column CD and CB. So the stiffness of both members to be added up, which is 4ei by 4 plus 4ei by 2. So 3ei. So this 1 3 1 3 k13, which is minus 1.5 ei. K21, we already have K12, so which is equal to minus 0.375 ei, minus 0.375 ei, and K11 1.6875 ei. So these are all the stiffnesses for the entire frame. So simply now taking the equilibrium equations, which is K times delta is equal to P minus PL. Now the question comes, what is P here? So P is the direct load applied, direct forces in coordinate direction. So if you look at our structure here, in our coordinate direction 1, I have a 50 kilonewton load in the same direction. So P1 will be taken as 50, and there is no external movement applied at the B or C. So P2, P3 0. So somebody may ask, how will that movement applied directly on the B? So there could be sometimes, some cases, overhang, and there may be a load like this. So this load into distance causes a moment. That will be a direct movement at third coordinate, that we can take as a P3, if at all like that is there in the question. So going, so the P1 is 50 kilometer and P2 equal to P3 equal to 0. So PL already we decided. So K, taking EI to be a common, 1.6875 and K12 minus 0.375, K13 minus 1.5 minus 0.375, which is 2, 0.5 minus 1.5, 0.5. So this is the stiffness matrix. This is the stiffness matrix for the frame multiplied by delta 1, delta 2, delta 3. So which is equal to the directly forces. This force is P minus PL. So I know the P was the 50, 0, 0 and PL was 0, minus 40 and plus 40. By subtracting the P minus, this is P. So P minus PL gives me the 50, 40 minus 40. Then taking this inverse method to know the 3 by 3 matrix inverse in the calculator. So taking the delta 1, delta 2, delta 3, taking inverse of this, I can find out delta 1, delta 2, delta 3, delta 1, delta 2, delta 3, which are nothing but, very important, which are nothing but my displacement at B and theta at B and theta at C. This is very important. Is equal to inverse of this multiplying this, by multiplying, taking inverse and multiplying this matrix. So you get a 1 by EI times 35.56, 26.67 and 0. So this is the displacement. So here we are finding the displacement first, then finding the force, and that's why this method is called displacement method. So once we obtain delta B, delta C, simply a matter of using the slope deflection equations, MAB is MFAB, since no moment there, MFAB is 0, plus 2 EI by L. L is a 4 meter, and 2 theta A is 0, plus theta B is a 26.67. So directly this EI get cancelled out. So we need not to write down that. So if you take EI is outside, get cancelled out. 26.67. Okay. Minus 3 delta by L. 3 into delta displacement into B is what we already got it as a 35.56 by EI. So 35.56 by L, which is 4. So this comes out to be 0. Somehow I am getting the moment here. So MVA can also be found out similar way. MFBA not there. So then 2EI by 4 2EI by L into 2 theta B means 2 times 26.67 plus theta A 0 minus 3 into 35.56 by L, which is 4, is equal to 13.33 kilonewton meter. So MVA is obtained. Then let us go to MVC. MVC, which is MFBC, we have as minus 40 plus 2EI by L is length is 4, 2 theta B, 2 into 20.26.67 plus theta C, which is 0. So, and BC do not have a displacements, I mean deflection, not a deflection. That's all. So this comes out to be minus 13.33 kilonewton meter. MCB, which is minus MF, MF it is equal to MFCB, which is 40 plus 2EI by 4 into 2 theta C 0 plus theta A and theta B, which is 26.67, course by EI will be there, get cancelled out. So this is equal to half of, I mean this half plus 40 is equal to 53.33 kilonewton meter, and MCD is a vertical this member. A, B, C, D is 2 meter, 4 meter and 4 meter. MCD is MFCD 0 because no external load on that, plus 2EI by L is 2 meter, 2 theta C 0, theta D 0, minus 3 into delta. Delta is equal to 35.56 by L, and is 2. So this comes out to be MFCD, which is minus 53.33 kilonewton meter. MDC is equal to 2EI by 2 MDC, 2 theta C 0, theta C 0, theta D 0. So minus 3 into 35.56 by 2 length, and EI there. So EI here also there, get cancelled out. Same, minus 53.33 kilonewton. So this is the movement produced at each of the ends of the frame. So now we can look at some of the frames and see how to identify the degrees of freedom. If the degrees of freedom are identified, things are very easy. You should understand the 3 important concepts I'll explain here. So if in a given joint, if a unit rotation is applied there, the moment produced at the same point is 4 EI by L. Of course, theta is 1. The far end fix will have a 2 EI by L far end movement, and the effect produced in the next. It's a movement. That is one. The second important thing is, because of unit displacement at this point, delta equal to 1, how much is the shear produced which is 12 EI by LQ. Very important. 12 EI by LQ, shear produced at the or shear required to cause the delta equal to 1. That's very important. This in the direction. Okay. Another one you should know that because of the unit displacement, how much is the moment produced? Same point, how much will you produce if there is same coordinate, the same point? So because of the unit displacement here, how much is moment produced? That already we know, minus 6 EI by L square. So if we know these three formulas, so we will be able to write down the stiffness easily. Now we will look at the identifying the degrees of freedom in each of these frames. So now let us say this frame here at joint A, degrees of freedom 0 because no translation and no rotation. Here 0, no translation, no this thing, no rotation. And B, this frame first of all it is non-sway, so it can only rotate. So 1, which is rotation. Here there is another rotation, so theta. Here because of hinge joint it has a rotation. So total 3 degrees of freedom for this frame. Right? Now come back to this frame. Again this frame is non-sway because of the fixity here and a hinge connection here. Hinge will not allow any translation, no sway. So degrees of freedom all restrained here. So degrees of freedom 0 here. Degrees of freedom is the rotation allowed here, theta is there. Here rotation allowed, theta is there. So total 2 degrees of freedom, or degrees of freedom equal to 2. Now come back to this frame. Since AB and CD are same length, the load applied is in the mid. That means geometry symmetry, boundary symmetry, and load is also symmetry. So it is non-sway. Non-sway. So here entire joint A is restrained, so 0 degrees freedom. Joint D restrained, 0 degrees. Joint B only has a rotation. Joint C has only rotation. So total degree of freedom is 2. Come back to this frame. This is a hinge joint. This is a hinge joint. Hinge mentioned here. So, and because of lateral load, there is a possibility of sway. So sway, that means there is a deflection. Each of the column can undergo. Very important. So that amount of displacement is important. So the displacement is something like this, delta here. So here being hinge, this joint will not have any translation, only rotation possible. At joint here, rotation and 1 delta. Here 1 rotation and 1 delta. Here no rotation, no delta, is 0. So, but because of the axial deformation in the member is not accepted, assuming this beam is rigid, so this delta is equal to this delta. So that is only 1. One of the delta is, so total 1, 2, 3 and 4. So 4 degrees of freedom. Degrees of freedom equal to 4. Similarly here, this is fixed, 0 degrees of freedom. Here fixed, 0 degrees of freedom. At joint, because of lateral load, it can have a sway, so 1 degrees of freedom. Rotation, one another, so this is delta. So this also, this column also will go to sides, it's delta. And rotation here. So 1, 2, 3, 4, but horizontal displacement both are same, so total degrees of freedom is 3. Okay, so we should also know how to find out the stiffnesses for each of the degrees of freedom. Okay, thank you.